In this video, I'd like to talk about some examples and notes just about big O notation. So the first thing to remember about big O notation is that it describes the worst case runtime. And this becomes really important in some of the examples I'm about to do, is that we always want to focus on the worst case runtime of our algorithms. That's literally what the big O of whatever this function, this notation is. This represents the worst case runtime. It's the upper bounds of the performance function, essentially. So the next thing is, even though it's great to know the best case, the worst case, and sort of average case running time of an algorithm, whenever we're evaluating algorithms, we always want to know this. The big O, we want to know the worst case runtime, because this is really what's most important to us when you're benchmarking two functions against each other. And even though one may have a better average runtime, if another one has if it has a worst case runtime that's worse, then it's just going to make your program even that much, not to use the word worse over and over again, it's just going to make your program that much worse. So you always want your code to be in the worst case running efficiently. The next thing, big O notation does not care. So it doesn't care about individual operations. And what do I mean by that? So if you have a function that takes some parameter, and inside this function, it does something like this. It just initializes a variable, set this thing is equal to 5, and it says a plus equals 1. And then it does like a, if we're in Unity, do something like this where it's like debug.log the value of a, and then a equals 12, and then return a, right? This function here is a constant time function. And this function compared to this other one over here, where it just returns 12, right? Both of these functions end up doing the exact same thing. Down here, it's setting a equal to 12. It returns that variable. Over here, it just returns this, the integer literal 12. These two functions are functionally equivalent. But both of these in big O notation are both constant time functions, right? Even though, yes, this one is slower than this one. But the point about big O notation is that it is based on n. It's based on the size of our input, right? It's based on the size of input. So what we really care about is how these functions change as n gets larger. Now, in these functions, our input is literally this number n, but it doesn't have to be this number n. It could be the amount of data being stored in our linked list, the amount of data being stored in our vector, the number of players we have. Our data, the size of our input, will change contextually based on what these functions or what these algorithms are doing. In this case, it's probably this value n, whatever this thing is doing. If we were to graph both of these functions as far as their performance, they'd probably look something like this, where n is increasing. If it starts from 0 and increases, here on our horizontal axis, and our vertical axis is the amount of time that it takes for these functions to operate. Well, now I'm just coming with arbitrary times, but the function on the left over here, this function, would probably, I don't know, maybe it looks something like this, right? So as the size of n increases, it always takes the same amount of time. It takes whatever this time is. We can put a number to it. Say it's 0.2 milliseconds or something, right? It always takes the same exact amount of time. The function over here on the right, this function I've underlined in purple, we can say that this one takes the same amount of time as well. And we can say this one takes 0.1 milliseconds, right? Say it's twice as fast. Obviously, I'm just pulling these numbers just out of thin air. Now, both of these graphs don't change based on the size of our input, right? They are both constant time functions. They both have a constant time complexity, which means that the graphs of these functions look like this. And yes, this one is slower, right? It does take more time. Obviously, it's higher up on this, on this time scale. But when we're comparing these algorithms to each other, we really don't care too much about that. Going from this to this is an optimization. That's a code optimization, right? Going from two graphs that may look something like this or this, typically, once you start getting into the other time complexities, linear, quadratic, so on and so forth, like those, it's no longer about optimizing your code anymore. When you're running into functions that look like this, it's no longer about optimizing your code to make these curves slightly less steep or more steep. They're still going to be steep curves. So really what you want to look at is the size of the input and how these functions increase and change their runtime based on the size of the input, right? I can't stress that enough. So in this example here, this function is constant and this function is constant. And so when we evaluate these things, yes, this one on the left is slightly slower than this one on the right, but when we evaluate these things against each other, we say that these things both sort of operate at a linear time complexity. And when we look at it in that view, we really don't have a preference between the two. These two run functionally, as fast as each other. And so we don't care about the individual operations. We don't care that this thing is doing, a whole bunch of, 5 or 6 operations, whereas this one's just doing one. We don't care. What we really care about is how does it change based on the size of the input, right? All right, so let's do some examples. First example. So I'm going to have a function, and inside this function, it's going to look something like this. So this is an integer pointer called array. There's an integer size, which we can assume is the size of the data that's inside that array. And then there's a value here. And then this function initializes a variable, count equals 0, does a for loop in I equals 0, while I is less than size, I plus plus, and then it does if a array subscript I is equal to the value, then count plus plus, and then return count, right? So what would the runtime of this function be? Well, let's break it down. The first thing, here's our individual operations. This is constant time, right? It's just taking a variable and adding one to it. This here isn't really adding anything to it, right? Our subscript operator, in this case, this is a function call, right? It's using the subscript operator. But in this case, what we're dealing with is a pointer to a built-in array. We know that this is a constant time subscript operator, right? It's just doing a couple simple pointer arithmetic. This is also constant time here. This portion, this for loop, right? This for loop, as our size increases, this loop is going to increase as well. So if we're to draw a graph of this thing where we have n increasing on our horizontal and we have time increasing on our vertical axis, this will look something like this, right? N increases linearly with time, or time increases linearly with n. This is going to be linear time complexity, right? So we have, actually I'll redraw this bracket here because it actually encompasses this whole thing, right? So what we actually, and then this is a constant time. So if we were to actually go and add this thing all up, right, we would have this constant time here plus this constant time times this constant time plus this constant time, right? And these are being multiplied because for each n, it's doing these operations inside. So it really would look something like this. We'd have big O constant time plus big O of n times big O of constant time, plus there's this one here, so like plus it would look something like this, right? Like pretty relatively complex. In reality, when we have this constant time, that just gets automatically eliminated. A constant time plus a constant time plus a constant time is the same thing as just having big O of 1, right? There's no difference. It's one operator versus two operators. And remember, we don't care the number of operators. That just goes away. A constant time times a linear time is just big O of n. So reality, this whole thing just becomes big O of n. That's it. This is linear time complexity. The really quick and easy way to look at this is, look, there's one for loop, and that's all it's doing. Right? One for loop that increases based on the size. All right, let's do some more. Okay, next example. Here's another function. It's going to take another array. It's going to have a size. It's going to have a value again. And then inside this function is going to do something like this. If size is equal to 0, then it's going to return 0. So we have a really quick early out here. And then we do another count equals 0. We'll have a for loop. Int I equals 0. Well, I is less than size I plus plus. And then inside this, another for loop for int j equals 0. Well, j is less than size. So we have another loop variable here, and then we do j plus plus. And then we do a little bit of logic here where we say if the array bracket I is equal to the subscripts array bracket j, and I is not equal to j, meaning it's not the exact same element, then we want to increase the count. So this is actually a really quick, let's see, boom, boom, just making sure my braces all line up. Cool, something like that. And then we have done here, return count. All right, this is a really quick function which, if you haven't recognized it yet, it's really just looking for duplicates and counting the number of duplicates, right? So it's looping through the array. For each element in the array, it loops through the array a second time from the very beginning, right? Starts at the 0 index, goes all the way up to the total size. So it loops through all of them. And if the two indexes are the same, it ignores that position, and it's comparing the array element at I compared to the array element at j. If they match, it increases the count. This function is counting duplicates. And then the other thing that this has is it checks if the size is equal to 0 and returns 0. So it's also got an early out here, right? So let's do some quick big O analysis of this thing, some quick runtime analysis. Well, here we go. We've got, this is constant time. This is also constant time, right? In this case, our subscript operators are just using our built-in array here. So it's going to be really quick. Those are also constant time. This for loop here, this inner for loop, starts at j equals 0. Well, j is less than size, j plus plus. Same deal as the last problem. This is going to increase linearly. As our size gets larger, this loop is going to take an equivalent amount of time. Your size is 10, this loop iterates 10 times. Size is 100, this iterates 100 times, right? This is going to increase linearly with the size of our input. The size of our input being the size variable in this case, right? The size of the data inside this array. All right, so let's look at this outer for loop. Same deal. This thing starts at 0, increases while it's less than the size, I plus plus. So nothing special going on here. Just like the previous couple, it's also going to be linear, big O of n. And then finally here we have this thing up at the top, right, which is actually constant time. This is just checking, it's doing one simple operation, comparison, and then returning 0. So the question is what is the runtime of this function? Well, let's look at this bottom part first. So the bottom part is, because of these cascading for loops, the bottom part is big O of n times big O of n, and that's times, big O, some constant stuff, right, which we actually end up not caring about. What we really care about is this. It's big O of n times big O of n. So we get something like big O of n squared. This thing, as you increase the size, it is going to create, because it's doing a double for loop, this thing is going to increase sort of exponentially. If you were to graph this, it would look something like this. It's going to get worse and worse over time. Far worse than something that's just linear. So the question is does this function end up being big O of n squared, or what about this thing up here, right? What does that mean? This function could run and it just exits immediately, right? Well, remember that big O notation is the worst case. We want to keep track of what is the worst case situation for this function. And the worst case situation for this function is this, big O of n squared. This function is big O of n squared, right? This portion up here doesn't matter. It doesn't matter at all. You can have whatever you want up here, and it doesn't matter because the worst case for this function is big O of n squared, right? All right, let's do another one. All right. Here's another function. We're going to assume that this takes a linked list. And we'll just call it, I don't know, ALL, sure. And then this thing's going to take a value. And then inside this function, it's going to do something similar. We have a count is equal to 0. We're going to do for int I equals 0. Well, I is less than, we'll just assume that there's some sort of size, a linked list dot size or count, whatever this function is to be able to get the size, and then the I plus plus. And same check as sort of like our first function is we're going to check the linked list subscript I. We're going to check if that is equal to the value. And then if it is, we're going to do a count plus plus, close out that, and then return count. So very simple. This is essentially just looping through a linked list, right? It's looping through a linked list, checking how many elements are equal to the value. It keeps track of a count that increases, and then finally we return the count. So it's just a function that's counting how many times does this value show up in the linked list. All right, let's do our logic again. Let's start here on the inside. This, big O constant time, right? There's really not much going on here. This line, well, we're just doing a subscript operator here. A lot of people would initially say, well, this is just big O of 1, constant time, and this is actually wrong. This is what trips up a lot of people. The subscript operator on this line, it's a linked list. And what do we know about linked lists and their subscript operator? They are not constant time like a built-in array. The subscript operator, even though this looks like one line of code, the subscript operator on a linked list is actually big O of n. It's linear in time. Remember that a linked list looks something like this. It's got a bunch of elements that are sort of connected to each other and pointing to each other. And then when you want to find an element that's later in this list, you kind of need to start here at the very beginning and then iterate your way through it, right? So using the subscript operator on a linked list is slow. It's one of the disadvantages of a linked list. So we end up with this, big O of n. Just for that one line, just for this one if statement, we have big O of n. Finally, our for loop, I is equal to 0, y is less than the size. Here's another big O of n, right? We have big O of n times big O of n. This whole function is big O n squared. That's the function. That's what it is. Excellent. Let's do another one. This function. This function is going to take another built-in array. And it's going to take an index. And it's going to return dereferenced array plus index. Nice and short. Well, what's the runtime of this function? What is it doing? The first thing it's doing, well, it's doing this addition, right, which is just a single operation. And it's doing it based on this thing, which is a pointer. This is just a memory address. And then it's adding an index, which is just an integer. This section here is just doing some very simple pointer arithmetic. Then what? Then it dereferences it. So that's it. That's all it's doing. What's the runtime of this function? Well, the runtime of this function is constant. There's really nothing special that's doing here. It's doing a really quick addition, some pointer arithmetic, and then it's dereferencing it, which is just another simple operation. In fact, this function is the subscript operator for an array, right? Remember that the subscript operator is the same as dereferencing a pointer plus an index, right? Which is what this is. It's the pointer plus the index. So here we go. This is constant time. Doesn't matter how big your data is, how big your array is, what the index is. This is always going to take the same amount of time. It's a constant time function. All right, let's do another one, another slightly larger one. All right, in this function, I've got an array, I've got a size, I've got a value, my count, I'm initializing to 0, for int I is equal to 0, well, I is less than size, I plus plus, for int j is equal to 0, well, j is less than size, j plus plus, right? So I have this double for loop thing going on again, right? Let's see, double for loop thing going on again. If a array subscript I is equal to a array subscript j, and I is not equal to j, count plus plus, close it, close it, close it, return count. These look really similar. This looks just like the other one that we did earlier. So just like the other one we did earlier, this all constant time, right? It's not much going on here. This is a built-in array, subscript operator. These are actually functions, remember, but built-in array, super quick, constant time. Let's see, this here, j is equal to 0, j is less than size. This just looks like big O of n, just another linear one. I is equal to 0, well, I is less than size, right? Another one, big O of n. That's it. There's nothing else really going on in this function. So we've got big O of n squared, right? Which is this big O of n times this big O of n. And that's it. Another pretty easy one. The double for loop, well, both of them are going from 0 to size. It's a pretty quick and easy one to spot. Big O of n squared. All right, let's do another one. This will be our last one. All right, another one with a built-in array. This one's going to take a size and a value. And then inside this, it's going to say for int I equals 0. Well, I is less than the size, I plus plus. And this is going to do something like this. If a array plus I is equal to a value, right? Is equal to value is what I called it. Turn true. And then finally return false. Okay, here's an interesting one. First, let's pick this apart. So this one here, this is just a return, right? That's obviously just constant time, right? There's really nothing special going on there. It's just one quick operation. Here, this looks like a subscript operator, except the long term, right? Or the long way to write it out. So we have our array plus our index, dereferencing it, and is that equal to value? So there's sort of three operations going on here. There's an addition, there's the dereference, and there's this comparison, right? But we don't care about the number of operations. This is still, this part here, constant time. Next, let's look at our for loop. I is equal to 0, I is less than size. Again, this is just going to be like that other graph, linear, increasingly. So big O of n. And that's pretty much it. This thing's also big O of, big O of 1, right? So, but that doesn't really matter. So that's pretty much it. So this looks like big O of n. This looks linear, right? Until you look at this, return true. So this function could be executing. And then in the middle of the function, if it finds a value that it likes, this thing could return true. This thing could just exit the function early. It doesn't have to run until the end of this for loop, right? So what does that mean? Well, for our big O notation, it means nothing. Remember that we're doing worst case, which means that we don't care about things like this. We don't care about early outs. We don't care about this function, the idea of it not running to completion, right? In the worst case scenario, this function runs 100% until it gets to the very end, until it gets this line here, right? So this is big O of n. That's the answer for this. Excellent. Well, I hope this video helped cleared up a couple questions about big O notation, especially sort of how you do some of the analysis. And that's it for now.